Welcome to the deep dive. We've got some really interesting source material today, stuff that looks at life itself, but from a physics angle.
That's right. It's asking, beyond the biology, beyond the chemistry we usually talk about. What fundamentally makes something alive, according to physics?
Okay, so it's a deep question. Our mission here is to really dig into these sources and pull out the main arguments. Why do they think living systems might need, I guess, a whole different kind of physics compared to, like, a rock or even a complex machine?
Exactly. And the logical starting point, really, is classical thermodynamics.
Right, the laws of energy?
Hmm.
Because that's where the standard physics view starts to look a bit shaky when applied to life.
It really does. I mean, the first law, conservation of energy, that's fine. Energy isn't created or destroyed, just changed. Living things follow that. No problem there.
Okay.
But then you hit the second law, the entropy law.
Entropy, disorder,
Uh,
randomness. And the law says that always increases in a closed system, right?
Right. Or stays the same, technically, in like a perfect theoretical process. But yeah, generally things tend towards more disorder.
And you see that everywhere.
Yeah.
Heat spreads out, it doesn't gather itself back up, ink mixes in water, it doesn't unmix.
Right. Machines wear down. It gives us this directionality in time, this arrow towards maximum disorder, thermodynamic equilibrium.
Which is basically a state where everything's uniform and, well, pretty dead, really. Nothing much happens.
And that's the clash, because living organisms are the opposite of that. They're incredibly ordered, dynamic, complex structures.
They maintain themselves, they build complexity, they fight decay.
Constantly active, constantly working far, far away from that static equilibrium state.
So from that classical perspective, they almost look like they're breaking the second law, like they're anti-entropic.
Well, they look that way, but the argument in the source isn't that they break the law, it's that the law, as usually applied, isn't the right tool. Classical thermodynamics was built for simple, homogeneous systems near equilibrium.
And life is
Yeah.
none of those things.
Exactly. It's complex, heterogeneous, and way out of equilibrium. So the source says applying that standard framework is just inadequate. We need something else.
A different kind of thermodynamics, like a thermodynamics of organized complexity, as they put it.
Precisely. And that involves rethinking some core concepts, like free energy.
The energy available to do work, which decreases as entropy increases.
Yeah. The source suggests maybe we should think more in terms of stored energy, energy that's held within the specific space-time organization of the organism itself. The organization is the capacity to do work.
Okay. So it's not just about the amount of energy, but how it's structured, how it's held.
Yes. And that leads straight to the next huge point, energy flow.
Right. Organisms aren't isolated boxes. They're open systems.
Totally. They take in energy and matter, sunlight, food, process it, use it, and then crucially, they dump waste heat and entropy back out into their surroundings.
And it's this constant flow of energy through this system that lets them maintain their order, yeah.
Yeah.
Keep things running far from equilibrium.
That's the key idea. These ordered states maintained by energy flow are what the sources call dissipative structures.
Okay, dissipative structures. Is there a simple example of that?
Well, the classic one used in the material is Bernard-Rayleigh convection. You heat a thin layer of liquid, like oil or water, evenly from below.
Okay.
At first, heat just conducts through. But past a certain point, a critical temperature gradient, and suddenly, wham! The liquid self-organizes.
Into what?
Into these incredibly regular, rolling hexagonal cells, convection cells. You get this beautiful macroscopic pattern.
Wow. From just uniform heating.
Yeah. And think about it. You started simple, uniform. Now you have this highly coordinated movement of like trillions upon trillions of molecules. The source mentions something like 123 molecules per cell, all moving in perfect synchrony across the whole pan.
That's amazing. Order just popping out of energy flow.
It shows that this kind of self-organization, this coherence, isn't exclusive to life. It can happen in physical systems driven far from equilibrium.
But the source argues that life's energy use is even more specific, right? It's not primarily like a heat engine.
Right. Heat engines, converting heat to work, tend to be pretty inefficient, thermodynamically speaking. Life seems different.
How so?
The argument is that life's core energy transactions are fundamentally electronic, electric, electromagnetic. It uses high-grade energy photons, chemical bonds.
Tapping into that deep physics connection between electricity, magnetism, and light that Maxwell figured out. Life lives in the electromagnetic spectrum.
A vast spectrum, too. The source notes it spans something like 73 octaves. Life is deeply embedded in this electromagnetic reality.
And this focus on electronic energy leads to the next big idea, that biological processes might actually be quantum.
Yes. That at the fundamental level, biological components like proteins and enzymes aren't just tiny classical machines, they're acting as quantum molecular machines.
Okay, hold on. Quantum. Isn't that usually about, subatomic particles and weird probabilities? How does that apply to something macroscopic, like seeing or flexing your bicep?
Well, the argument comes from looking at the sheer efficiency and, maybe more importantly, the coordination we see in biological processes.
Give me an example. Vision.
Fission's a great one. A single photon hits a rhodopsin molecule, triggers a whole cascade. We know the molecule's involved, sure, but the speed,
It's fast.
incredibly fast. And the amplification, one photon signal gets massively boosted, activating hundreds of other molecules in maybe milliseconds. Trying to explain that just with classical molecules bumping around randomly, simple diffusion, it feels too slow, too random. The source suggests there's something more going on, especially involving the cell membrane's role.
Okay. What about muscles?
Muscle contraction is maybe even more striking. You've got these tiny myosin protein heads grabbing onto actin filaments, pulling, letting go, grabbing again. That's the molecular level.
Driven by ATP, the cell's energy currency.
Right. And the source points out we're talking vast numbers, something like 10 to the power of 19 ATP molecules split for one muscle action. And all these little molecular motors, millions of them, have to work together almost instantly, perfectly synchronized.
To produce movement over huge distances, relatively speaking,
Yeah.
from nanometers at the molecular level to, centimeters or meters for your whole arm.
Exactly. That's like 9 orders of magnitude difference in scale. And they convert that chemical energy into mechanical work with almost 100% efficiency.
Okay, yeah. Getting that many tiny parts to work together so perfectly, so quickly, and so efficiently. Classically, that seems hard to believe. Like, it would require impossible coordination.
It's incredibly difficult to model classically without invoking some coordinating principle. And this is where the source introduces coherence.
Coherence,
Yeah.
meaning things acting together in step.
Yeah. The idea is that these quantum molecular machines aren't acting independently. They're coordinated by some underlying principle, and the argument is that this principle is quantum coherence.
So the organism itself is seen as a kind of coherent space-time structure.
That's the picture they paint, yes.
Okay, let's unpack quantum coherence a bit without getting totally lost. We know basic quantum ideas like wave-particle duality.
Right. Things can be waves and particles. And then there's the really weird stuff like entanglement and non-locality.
Where two particles can be linked, even far apart, and measuring one instantly affects the other.
Sort of, yeah. In a simplified sense, it points to a kind of unity, where separated parts still behave as part of a single correlated system. Quantum coherence describes a state where parts are globally correlated, acting in concert, even while they might have some local independence.
And the source uses this term factorizability. What's that about?
It's a specific property they associate with coherence in living systems. It essentially means the system achieves both maximum local freedom for its parts, cells, molecules doing their thing, and maximum global correlation or cohesion. Everything works together seamlessly, but without rigid central control.
The best of both worlds, in a way. Local autonomy and global unity.
You can put it like that. It allows for flexibility and integration simultaneously.
Is there actual evidence pointing to this kind of coherence in living things we can observe?
The source cites several lines of evidence. One is just the pervasive nature of biological rhythms.
Like circadian rhythm, sleep-wake cycles.
Yes, but much more too. Rhythms across incredible timescales, milliseconds for nerve firing, seconds for heartbeats, minutes, hours, days, even years. And across spatial scales, from single cells coordinating to whole populations.
And these rhythms are often coupled together.
Very tightly coupled, sometimes across vastly different timescales. The source mentions examples like fruit fly circadian rhythms being linked to their wing beat frequency, that's a huge difference in timing, or the precise coupling between heart rate and breathing. This suggests a deep underlying coherent order coordinating these cycles.
Okay, what else?
Another big one is the extreme sensitivity of organisms to very, very weak electromagnetic fields.
Weak how?
Fields with energy levels way below the energy of thermal noise, KT. The random jiggling energy of molecules at body temperature. Classically, any signal that weak should just be drowned out, lost in the noise.
But organisms respond.
They do. The source gives this really startling example. Static magnetic fields, like fields weaker than the Earth's magnetic field, affecting how patterns form in developing fruit fly embryos. The energy involved is something like 5 orders of magnitude, 100,000 times smaller than the background thermal energy.
Wow. How could that even be possible classically?
It's very hard to explain if you think of molecules just reacting individually. It strongly suggests some kind of, yes, and things like polarization and frequency. Static fields, for instance, can influence chemical reactions involving radical pairs by affecting electron spin. These are important in many biological processes. Oscillating fields might resonate with specific biological frequencies. And static fields might even physically deflect tiny electric currents crucial for development. It's complex.
Okay, any other evidence for coherence?
Biophoton emission, this ultra-weak light that living things constantly emit.
Like a faint glow.
Extremely faint, yeah. But studies on its properties, like how the light decays after a brief excitation is called delayed luminescence, show characteristics that don't fit simple, random molecular relaxation.
How so?
The decay isn't smooth and exponential, it's often hyperbolic, nonlinear, and energy seems to get stored and redistributed across the spectrum very quickly. This is consistent with the energy being stored in a collective, coherent photon field within the organism, not just individual excited molecules.
Work by Musumeci and others, the source mentions, suggesting this coherence gives the system almost a single degree of freedom.
Exactly, reinforcing that idea of global correlation alongside local variability.
And finally, there's the actual physical state of the stuff inside us. It's not just water with molecules floating around.
Not at all. The source emphasizes the liquid crystalline state of living matter.
Liquid crystal, like in an LCD display.
Similar principle, but biological. It means it's highly ordered, but still fluid and dynamic.
Yeah.
Most of the water in cells, maybe 70–80%, isn't free water. It's structured, forming ordered layers around proteins, membranes, the cell's internal skeleton.
So everything's interconnected and organized.
Pretty much. The source cites experiments, like spinning cells really fast in the centrifuge, which found hardly any free large molecules floating in the watery part. It suggests almost everything is part of this structured, interconnected matrix.
And this liquid crystalline structure is seen as the perfect medium to support those coherent quantum excitations, like the Fröhlich state mentioned.
Precisely. Things like collagen, with its aligned fibers and bound water, are highlighted as examples of materials perfectly suited for this kind of long-range coherent energy transfer and storage. The physical structure enables the coherent dynamics.
Okay, so this whole physics perspective, it really shifts things. It seems to have implications beyond just molecules and energy.
Oh, absolutely. It starts to touch on really deep concepts, like information and knowledge.
How does that connect?
Well, there's this idea, going back to physicists like Brillouin, that entropy isn't just disorder, it's also related to a lack of information about a system's detailed state. The more you know, the less entropy you perceive.
And gaining information costs energy.
Often, yes. And the source makes this intriguing point that the observer's knowledge can actually seem to change the physics, like how much work you can theoretically get out of a system or even its calculated entropy. It depends on what you know about its initial state.
That's pretty mind-bending. Blurring the lines between objective reality and the observer.
It does. And it also leads to thinking differently about time and living systems.
Not just a linear clock ticking.
Maybe not. The source talks about biological processes catenating, linking together, propagating effects and structures forward in time, creating a kind of embodied memory.
Related to that coherence, time, and volume, the duration and space over which these coherent energy transfers happen.
Exactly. The huge range of biological rhythms spanning maybe 10 orders of magnitude in time is seen as reflecting this structured, non-simple nature of biological time.
And inevitably, this line of thinking bumps up against the really big questions like consciousness and free will.
Yeah, the source definitely goes there. It speculates that maybe these phenomena aren't separate ghosts in the machine, but could be emergent properties of this unified, liquid, crystalline, quantum coherent physical system that are the organism.
And that specific property of coherence factorizability, allowing local freedom within global unity.
This is suggested as possibly mapping onto our subjective experience of having individual free will while still being a single integrated self. It aligns with a view where consciousness isn't just observing reality, but participating in it.
So summing up, this isn't about having all the final answers on what is life.
Not at all, but it's offering a fundamentally different physical framework, a new lens to look through.
Right, it's a shift away from seeing life as just a very, very complicated classical machine.
Towards seeing it as a dynamic, highly ordered, fundamentally coherent system operating far from equilibrium, probably utilizing quantum effects in crucial ways.
Okay, so we've really covered a lot of ground in this deep dive. We started with that basic puzzle. Classical thermodynamics predicts disorder, but life creates and maintains order.
Yeah, and we saw how continuous energy flow, especially high-grade electromagnetic energy, is key to sustaining life's far from equilibrium state, creating those dissipative structures.
Then we explored how the incredible coordination and efficiency seen in things like vision and muscle contraction point towards something beyond classical mechanics, leading to the idea of quantum coherence.
Right, coherence as the potential organizing principle, supported by evidence like biological rhythms, that amazing sensitivity to weak fields, biophoton emission, and the liquid crystalline nature of living matter itself.
And we touched on the profound implications how this view might change our understanding of information, time, and maybe even the physical basis of consciousness and free will.
Seeing the organism as a unified, coherent entity.
So here's a thought to leave you with as you go about your day. Just consider, what if the processes keeping you alive right now, the very fabric of your being, aren't just complex chemistry, but involve deep physical principles like quantum coherence, maybe even non-locality? How might holding that possibility change how you think about your own body, its sensitivity to the environment, especially the electromagnetic world, or your connection to everything else? What does it mean if life isn't just complicated, but deeply physically coherent?